Okay, so welcome everyone. We're happy to have Ed Richmond from Oklahoma State telling us about smooth-like adjacent permutations.
Great. So thank you for the invitation. It's an honor to be able to speak here. So today I'm going to talk about what I'm calling smooth-like permutations. And so this is, I put smooth-like in my title that I submitted to Leonardo, and then afterwards I realized that adjacent is probably a better word. So what I'm going to do is, and also this is, a lot of this discussion will be like Christian's in the sense that it will be a survey of many results, many that are not my own. But then there's some stuff, there are some parts of the story that I'm involved with, and that stuff is joint work with my student, Fakhruddin Azam, and separately with William Slofstra. So let me kind of get started with some of the objects. So and by the way, this talk will be exclusively type A, but some of the parts of the story generalize to other types. So I'm going to define the flag variety. Well, actually, before I define the flag variety, I'm going to fix a vector, a complex vector space that will be the span of some coordinate vectors. And then I'll define the flag variety, complete flag variety, to be just, sequences of nested subspaces such that the dimension of each space is given by its index. So this is, the classic type A flag variety. And with respect to the spaces, there's a particular distinguished flag, and I'm going to write it like this, an arrow above. So what this means is basically like you take the flag that is the span of E1 containing the span of E1, E2, containing the span of E1, E2, E3, and so forth. So that creates an element of the flag variety. And this point has a stabilizer inside GLN-C. So GLN acts just in the standard way on CN, so it acts on the flag variety, and this point has a stabilizer. In matrix terms, this is simply the classic model of upper triangular matrices, where upper triangulars corresponding to the standard order. And for any permutation on n letters, or on the numbers 1 through n, we can define the flag, W1, W2, Wn. Like this. So all you're doing is simply you're permuting the coordinate vectors by this permutation, and you look at the corresponding flag. With respect to the action of diagonal matrices, the torus here, these are precisely the fixed points of the flag variety. You get one for each permutation, and there's a Schubert variety. So the Schubert variety is just defined to be closure of the orbit of B. Of this fixed point right here, and this is of course sitting inside the line. Okay, and some facts about some quick facts about this thing is first, the dimension. It's fact 1. Dimension XW is given precisely by the length of the permutation, which is defined to be the number of conversions. And the second fact is that these Schubert varieties have a nice cell structure given by Brouat order, where you look at, so the B orbits are called Schubert cells. And in fact, so this is called Brouat order or Brouat-Chevalier order. And you can even define it by just, sitting in the closure of these things. So These varieties, I mean, this is, I'm sure all you guys have been talking about Schubert varieties nonstop. So I don't have to convince you that, there's a lot of interesting geometry and combinatorics and surrounding these varieties. So the question that I'm going to be focusing on today, this is the second board, yeah. It's the following question, or one of the questions, for which permutations is XW smooth? And then the follow-up question, since I like combinatorics, how many? Okay, and this question, throughout the years has had many different answers, and many of them quite really beautiful. And in a moment, I'm going to summarize the ones that I want to highlight. And then what I'm going to do is I'm going to talk about other types of families that are related to smooth Schubert varieties that have sort of analogous equivalent descriptions. And then in the end, what I'm going to do is, so there's going to be smooth, and what I'm going to do is I'm going to talk about two families that are going to be subcases of smooth, and then two other families that are going to be slightly larger than smooth. And they're all going to have sort of a similar outline. And then after I sort of give all these outlines, I'm going to tell you sort of a single combinatorial model that kind of captures all five families at once and tell you, and sort of convince you that this is like a good way to think about these families of Schubert varieties. So that's my goal. That's my goal. And I'm going to do my best to try and attribute everything to who it's due, but I might have mixed up a few things. So, and all these theorems are going to start the following. And by the way, if you have any questions, feel free to just shout, and I will be happy to stop and answer questions. So the following are equivalent. So the first one is XW is smooth. XW is smooth. The second is going to be probably the most famous. It's given in terms of pattern avoidance on the one-line notation. This is due to Lakshmi and Sandaya. So W avoids the patterns 3, 4, 1, 2 and 4, 2, 3, 1. So this is due to Lakshmi and Sandaya. Abbreviate it. So if you don't know much about pattern avoidance, so what does it mean for a permutation to contain a pattern? It means that there exists a sequence in the one-line notation of W that has the same relative order as this pattern. So for example, this one, it means you have you can find 4 numbers such that the first one is the third biggest, the second one is the biggest, the third one is the smallest, and then the last one is the second smallest. That means you contain a pattern. And if there exists no such subsequence of W, then you avoid the pattern. So pattern avoidance is is sort of very easy in terms of conceptually easy, and it's also computationally easy. If you're given an arbitrary permutation, doesn't matter how big it is, you can simply check. Well, it does matter how big it is, but you know what I mean. But you could get n could be 500. And you can check to see if you contain such patterns, and that would be sort of difficult geometrically. Okay. Next condition.
And, but by the way, I recently learned this, that you can do that efficiently.
Oh.
ON time.
Oh, nice. Nice.
N is the 500.
Okay. Nice. Yeah. So all the families will have a pattern avoidance characterization. So this is the bonus about pattern avoidance. Okay. The next condition is going to be, if I look at the Brouwer interval. The Brouwer interval is rank symmetric, which means you have this. This is a partially ordered set. It's graded by length, so it has a rank. And rank symmetric just means that the number of elements of you look at the top and bottom, and if you flip it upside down, those numbers form a palindrome. the number of elements of each rank. This is kind of hard. I think this is maybe due to Gacharov. But I'm also going to throw in Carol Peterson. Where they study the symmetry of these things, and there's a notion of rational smoothness, and what Carol Peterson shows that for simply laced flag varieties, the smooth locus and rationally smooth locus coincide, and rationally smooth things have rank symmetric Brouwer intervals. Okay, so
that's not true in general.
The lower intervals are not necessarily rank symmetric.
I mean, if it is symmetric, is it smooth?
For simply laced, yes. For non-simply laced, no.
Oh, still.
Yeah. Rationally smooth. But rationally smooth is equivalent. Rationally smooth is equivalent to having this interval being rank symmetric. Yeah. Okay. Yeah. 4 is going to be. This one is geometric. Okay, IFB stands for iterated fiber bundle. Iterated fiber bundle of Grassmannians. Grassmannian varieties. What this means is, there's going to be a sequence of, you can induce there's a sequence of projection maps starting with the Schubert variety, where the fiber at each projection is isomorphic to a Grassmannian because it's a fiber bundle. Grassmannians are smooth. Fiber bundle, put them all together if this is smooth. It turns out that every smooth Schubert variety in type A has such a fiber bundle. This is due to Ryan in 1986, like this.
In some unique way, or can it?
Yeah. This is good. So when I talk about iterated fiber bundles, all fiber bundle structures will come from taking your full flags and forgetting vector subspaces. So you have natural projections. So this is G mod B. You can project onto any G mod P. When you project onto G mod P, flag-wise, that means forgetting subspaces. So for example, if you forget everything but V4, that's projecting onto the Grassmannian. So this iterated fiber bundle comes from, take the flag variety, forget a sequence. So pick an ordering on 1 through n, and forget those spaces one by one as you go through. What Ryan proves is there exists a sequence. There exists a sequence such that when you take those sequence of projections and you restrict it to the Schubert variety, that will have this. It will have this property. Not every sequence will work, but if you're smooth, there exists a sequence. It will work. And when I say iterated fiber bundle, I'll only refer to fiber bundles coming from, I'll call these like parabolic fiber bundles, where you forget subspaces. So there's nothing fancy about these fiber bundles in terms of like where they're induced. They're always going to be induced by forgetting vector subspaces.
But sometimes more than one way.
Oh yeah, like if you take the full flag variety, any order will work. Yeah, and if you take this order, then your things will be P1s. But if you take a different order, you'll get Grassmannians. Yeah. So it's definitely not. Yeah, there's not just one, but there is one. And one more. This is not really characterization. So I asked this question: how many? And my answer to how many will be a generating function. The question is there a generating function that counts the number of smooth permutations of Sn? And the answer, it turns out the answer is yes. And this is due to Haiman. And I'm not going to write down the generating function because I don't think it's very useful in a talk, and I also don't have it written here, so I couldn't even tell you what it is. But here's what I want you to know. So what does Haiman do? What Haiman does is he looked at Ryan's result. This is an iterated fiber bundle of Grassmannians, and he studies this iteration and basically takes advantage of this structure and calculates the generating function. That's if you look at his proof. He never published this, which is semi-frustrating. But the preprint exists. You talk to the right people, and you know, and I've seen it. Yeah, and this is exactly what it does. The sharing function was calculated by boosting a little later using different structures. What that other paper is more of a pattern avoidance thing, more of a pattern avoidance thing. Calculate the generator function using pattern avoidance. But Haiman uses the fiber bundle structure.
Following are equivalent to the fifth item is yes. How do you read it?
Oh yeah. It's not. This 5 is not part of the list. Sorry.
So the 5 means it has a generating function?
Yeah. Five will be the answer to the question, how many? So yes, generating function is no.
There's only one way to counter this thought.
Yeah, generating function. So yes, this is the question. Is the generating function known? Yes, it is. Yeah, and it's not bad. It has like a so it's not quite rational. It has a square root in the numerator, but square root is very gentle in terms of generating functions. Like Catalan numbers have a square root in the numerator.
But it said someone asked like what percentage or.
Yeah. So you can figure out the growth rate. So permutations grow n factorial. Smooth permutations grow at roughly 4 to the n. So it's a small value. It's not exactly 4. It's like 4 point something. But and you should expect that, like when you have very large permutations, it's very difficult to avoid those patterns. You know, it's a very strong condition. So most things are not going to be smooth.
Is there, like, you have a list of finite list of patterns. Is there some way to generate the generating function?
Not a universal way. This is a big industry in the permutation patterns. Is like you want to count the number of permutations that avoid patterns. In fact, there's a famous list. So when you look at pairs of length 4 patterns, there's one pair. There's something called Wilf equivalence, where you know if you avoid these patterns, then you rotate the symmetries of the permutation matrix will give you, like, if you know one, you know the others. There's one Wilf class of length 4 patterns, pairs of length 4 patterns that no one can calculate the generating function for. And it's probably the biggest open problem in permutation pattern for the permutation pattern people. And it's really weird.
It depends on the growth rate. Surely it must always.
Yeah, I think there are a lot of papers out about like the asymptotics and all these other things, but I don't know the details. Yeah, but all other pairs of length 4 patterns, you know, they know the generating function, a lot of the details, but there's just this one pair that's a bit second. Yeah. Okay, so this is what I'm going to sort of reproduce. In some cases, not all the components, but I want to talk about like sort of the first class. We're going to use these sideboards. Okay, the first class is going to be a subclass of smooth, and that's going to be toric. So you can prove that any Schubert variety. Actually, this is in general. I think any Schubert variety that's also a toric variety is smooth. So it's going to be a subclass. So and I'm going to have a following theorem.
G mod. You're always G mod B, right?
Yeah, G mod B. I'm only G mod B. Yeah, only G mod B. Okay. So the following are equivalent. One. That's W, the toric manifold. Counterpuncher may prove that the reduced word given by these elements that are always a Coxeter element, which means that any reduced expression is a product of distinct simple reflections. So for example, like, you know, 1, 2, 3, or, you know, 2, 3, 5, something like this, where simple reflections don't repeat. Okay. So 2, pattern avoidance. W avoids 3, 4, 1, 2, which is the same as that 3, 4, 1, 2, and 3, 2, 1. Avoiding 3, 2, 1 is very difficult. It means you can't go down twice. So this is very extremely restrictive, like this. This is due to bridge tenor. Three. The Brouillard interval is Boolean, which should make sense because, you know, if a reduced word is given by product of distinct simple reflections, then subwords are just given by subsets of those distinct reflections. And, you know, we'll get no cancellations, so you get something that's Boolean in nature. I don't think that one is due to anyone. 4. XW is an iterated fiber bundle of P1s. Iterated fiber bundle of P1s. In fact, there's something a little bit stronger, like if you, these are precisely the Schubert varieties that are isomorphic to their Bott-Samuelson resolution. They're Bott-Samuelson. So Bott-Samuelsons are, you know, by definition, iterated fiber bundles of P1s. And these are iterated fiber bundles of P1s, and they're the same. They're the same. So, for example, you don't get any, you don't have any braid moves in this world because you have product of distinct reflections. So there's no way to get like different Bott-Samuelsons in this case. And then the last one, which is not equivalent, but the generating function, the answer is yes. You know, there is a generating function, and it's not a. That's also not due to anyone. That's like pretty. There's a order 2 linear recurrence, you know, which means you can just do it. Yeah. Yeah. Okay. So that's the first family that's sort of a subclass of this thing. And it comes from, you know, you can think about it as sort of a geometric subfamily.
Oh,
Yeah.
so this is for when it's toric with respect to,
The standard T action.
because in general, there's.
Oh, yeah.
There's a,
Yeah. Okay. Yeah.
in my opinion, a more significant difference.
Yeah. Yeah.
That characterizes for any toric.
Yeah. So this torus only. This torus only. Yeah. Okay. Yeah. Thanks.
There's also a theorem for that.
In type A, there's a theorem. So the question is like, okay, what does statement 1 mean? Here, statement 1 means with respect to that torus.
Yeah.
But in general, you ask, is it a toric? Right? In type A, there's.
Oh,
Yeah. So yeah, this talk is very restrictive. The fiber bundles are only those projections, and tori actions are only this torus. So that's the rule. Okay.
Is this generating function thing written down, or it's also not written down?
Yeah, it's right. You can find it in like the integer encyclopedia. I don't know if it's actually written. It is written down somewhere. I don't know. It might be in Bridget's. It might be in Bridget's paper. I don't know, but it's really, it's pretty easy to calculate.
Okay.
Yeah. Okay. Okay. Next subcategory is something called polished, which is a term coined by Christian Getz and Yibu Gao. And I'll tell you what it is. So polished feels like it should be a subcategory of smooth, because polished is, you know, better than smooth. So this is what they said.
very smooth.
Yeah, extremely smooth. So this is what so the first one is, you know, vacuous because we don't even know what this means. XW is polished. I will tell you 3 what it means. It means that the interval, the Brouillard interval, is self-dual. Self-dual. So if you're rank symmetric, that simply means that the number of elements on every level, when you turn them upside down, is invariant. Self-dual means that the poset, when you turn it upside down, is the same. It's isomorphic to its dual poset. And this is something stronger. If you're self-dual, then you're obviously rank symmetric. But it turns out this is a much stronger condition. Oops, sorry. It's a much stronger condition. And this kind of actually surprised me that it's a stronger condition. And in their paper, they give a pattern avoidance criteria for this. So what are the patterns? First you have to have the smooth patterns. So 3, 4, 1, 2, 4, 2, 3, 1. And then you have 4 more patterns, which I'll list like this. There are 4 length 5 patterns. What do I mean by this? I mean this pattern and its inverse as a permutation. So there's this one and this one. If you're smooth and then you avoid these two lists, then that corresponds to being self-dual in terms of pattern avoidance. But their paper is purely combinatorial. They did not discuss part 4 and they didn't discuss part 5. So
Who is they?
sorry, this is Getz. Gao. Getz and Gao. Christian Getz and Yibu Gao have if you look up like self-dual permutations, then you should be able to find their paper on the archive, and it's been published. I think it's like 2023, something around there, 2024. Yeah, but they don't address the fiber bundle. So this is a subcategory of smooth because it's here. And the question is like, okay, what are these? So it has a fiber bundle structure according to Ryan. So the question is like, what in the world is going on here? So Ryan says Grassmannians, these are P1s. What are these? So I'll get to what these are. This is my joint work with Azam. We studied this. And then once we did this, we also followed Haiman's result and we found a generating function for this last one. And it's quite nice. It's 100% rational. And I don't think it involves more than like degree 3 polynomials. So it's very nice. But I'll sort of get to this. I'll get to this a little bit later. Okay. So those are the subcategories. Those are the subcategories that I want to talk about. Now I want to talk about some soup categories. Some categories of Schubert varieties that are singular, but not too singular. Not too singular. And these categories don't have names, so the one is kind of going to be dropped from these. So
the question mark is the suspense.
yeah, that's the suspense. That's going to keep you awake. So what is this? What does it mean to be self-dual?
Item 1 could be the audience participation we suggested.
Oh yeah, that's just a name. Okay, so 1. Okay, so what should this 3rd category be, or what should this 4th category be called?
Right, before you go to, am I right in guessing that this is actually contained, toric, every toric one is polished. Is that right?
Yeah, every toric is polished.
So there's like, now we got a chain of.
Yeah. So this is inside this and this is inside this. Yeah, I didn't think about that. I just thought of them as separate categories. So yeah, you're right. Every toric will be polished. Yeah, because Boolean, you can flip it upside down. Yeah.
See the pattern avoidance too.
Okay. Yeah. Okay. And also for these soup categories, I don't have an analog of number 3. So I'm going to just give you a 2 and a 4. So this is the first one. So XW is an iterated fiber bundle, getting only by these parabolic projections. Grassmannian Schubert varieties. Okay. So Grassmannians themselves are Schubert varieties, but what you could impose is you don't want, you want to consider these fibers, and you want them to be Grassmannian Schubert varieties instead of just Grassmannians. And it turns out this has a pattern avoidance condition. And it's the following. And this is due to myself and one of my undergraduate students, Tim Holland, showed that that W has to avoid these patterns. So the 3-4-1-2 sticks around, just like the smooth case. But the 4-3-2-1 gets weakened to this length 5 pattern and this length 6 pattern. And what's interesting about this is this is the first, this permutation is equal to its own inverse. You can see that it's just two transpositions. This one is actually not. That one's not equal to its own inverse. So all of these categories are sort of closed, like these patterns are closed under inverse, which means the set is, invariant under, which means that, if XW is polished, then XW inverse is polished. So same thing, if X is smooth, if XW is smooth, XW inverse is smooth. This one's not true. So this one is not invariant under inverse. So it's a little bit different.
Grassmannian Schubert varieties aren't invariant.
Yeah. So this is a problem. Yeah. Yes.
Can you say, like, is there, do you know geometrically, like, is there a relationship between the Schubert variety for XW and W inverse?
They share the same local properties, but so like smoothness is shared between them, but they're not isomorphic. And they have, I mean, if you look at the Barreau, like their Barreau intervals, are the same. So a lot of their sort of coarse topological information is different, but you can just get different things.
But if you have a G-orbit Schubert variety, that would project onto each of these, and both would be a fiber bundle with bundles G mod B. So they both are. There's a total space which fibers over each of those separate spaces where the fiber is.
Yeah. But they're not the same. They're not the same. Probably the easiest way to see this is type C S1 S2 and S2 S1 are inverses of each other, but they're both Schubert surfaces of different index. So they're just not the same. And and in type A, even in type A, they're not the same. Like the first example of them not being the same is this one versus this one. Those do not give you this. Those are both toric, and they do not give you the same. They're not algebraically isomorphic to each other. Yes.
You don't take inverse of that guy?
What's the inverse of this?
It's not itself.
It's not itself.
You don't, but that one is fine.
Yeah, if you avoid these 3 patterns, then this happens. So these are equivalent. But if W avoids the patterns, then W inverse may not necessarily avoid the patterns.
Right.
And the first example is this one itself, or the inverse of this one. You can show that it avoids those 2, and it avoids this one with length 6.
Right.
But if you flip it, then now it contains this pattern, so you're ruined.
Can I ask the obvious question?
Yeah.
Fiber bundle of inverse Grassmannian Schubert varieties?
It's a fiber bundle of.
If you do it down to that.
Yeah.
So if you, what are you asking? Like you want to do something with this guy? And you want to do a fiber bundle on that?
No, I want the fibers to be inverse Grassmannian Schubert varieties.
Oh. Yeah, I don't know. I don't know what that, I don't know. I mean, so again, my fiber bundle is coming from forgetting vector spaces. So, so if you don't avoid these patterns, then if you contain one of these patterns, what this means is that like no matter what sequence you take, and you do this projection, you restrict it to this Schubert variety. Like one of those maps will not be a fiber bundle. At least one of those maps will be guaranteed not a fiber bundle, in the sense that the fiber dimensions will actually jump. So it's a very hard no in terms of the fiber bundle structure. Yeah. Now, if you could come up with like a tricky way to project in a different way, like I don't know, like you forget things in like a Richardson kind of way, or like you forget things like in a sneaky way, then maybe you could fix it. Oops, there's a lot of stuff on this thing. Yeah. But yeah.
Sorry to keep.
No, that's fine.
Do you know what the essential sets are? Like that's maybe 4.5, another thing you could throw in.
Yeah, I don't know the essential sets. if you avoid these? That's a good question. Yeah, I haven't thought about what the essential.
That's specifically this one.
This one looks like this.
Oh, you draw out the matrix.
Yeah, and then the 5, 2, 3, 4, 1 is dominant.
So I don't know what to call these, in terms of like, what this is, but we'll do Grassmannian. Sure. Okay. Let's leave that. Pretty understand. Okay. And then the 5 is I couldn't do it. So I could not figure out the generating function for this. And I'll tell you why in a little bit in the unifying theory I couldn't. So the answer is not. The answer is no, I couldn't do it. It doesn't mean that someone couldn't do it. But yeah, this was very difficult. So unknown at this point.
Okay. I don't know if you can answer this, but like 3, 4, 1, 2 is a Grassmannian permutation. So why isn't it a?
It's not.
3, 4, 1, 2 is Grassmannian here.
Yeah, so why is that not an iterated fiber bundle of Grassmannian Schubert varieties?
Because I'm not taking it, I'm taking it in G mod B, not G mod P. So this is a singular Schubert variety, and G mod B,
Okay.
and it's yeah, it doesn't. You try and forget. So you have V1, V2, and V3. Try them in any order. There's not too many of them, and it gets ruined. It's ruined no matter what.
That one maps by rationally to the Grassmannian itself.
Yeah, it maps birationally to the Grassmannian 2/4. But yeah, but it's in the boundary where everything is ruined. So yeah, these forgetful maps are B equivariant. So on Schubert cells, the fiber is always the same. Fiber is always the same, so it will be precisely on the boundary that things get ruined. Okay. All right. Okay. Last collection, and then we'll try and get. Okay. So one thing to note before I say this last one. Every Grassmannian has a unique Schubert divisor. And it's either given by a single box or a rectangle minus a box, depending on your worldview. So you have these codimension. You have the single codimension 1 Schubert variety living in a Grassmannian. So the last theorem will be 1. I don't know. I don't have a name for it. 2. What was 2? Yes, there is a pattern avoidance. 3. This is the. I don't have a 3, and 4 is going to be XW. An iterated fiber bundle of Grassmannians or Grassmannian Schubert divisors. Iterated fiber bundle of Grassmannian or Grassmannian Schubert divisors. And this work is due to my student Azam because I asked him to do this and it was too hard. So this is what he was able to do. And there is a pattern avoidance. W avoids 3, 4.2, 5, 2, 3, 4, 1. And then so these two come from there, and then you get the length 6 turns into 2 length 5s. Turns into 2 length 5s, and this completely classifies this scenario. And the answer here is yes, he was able to get a generating function as well. So so corollary in the pattern avoidance world, generating function for this list through the geometry of Schubert varieties. So these are the 5 families. These are the 5 families. And how am I doing on time? Probably doing really badly on time. No, okay. So let me tell you quickly kind of what unifies all 5 of these pictures. And it's something called a staircase diagram. Staircase diagram. And these are just very combinatorial in nature. They're not so bad. So we're gonna let I don't know if I'll use this, but let's end this. Let's just be the integers 1 through n. And I'm going to define D to be a sequence of intervals. So this is the rule. I want BI to be an interval here. So it's going to have a left endpoint and a right endpoint given by 1 through n. And I want these to be sort of like, I want them to be shifting over. So I want that, the LIs are strictly increasing. And I want the RIs, and I want the RIs to be strictly increasing as well. So they're shifted over. And so they don't contain each other. But the shifts could be, very large. They could be, disjoint like this. These intervals are going to form the steps of a staircase. Steps of a staircase. So I need to tell you basically how to stack these because steps can go down, they can go up. And so what are the rules? So I'm going to put a partial order on this. So definition. So D with a partial order is a staircase diagram. If two things. So if BI covers, so what's it covering? What's it covering in this relation? Covers are given by the following. So covers can be given, they have to be given by adjacent things. So the covers are going to be given by blocks, next to each other in this order. Right here. So this just means that when I go to the next one, I'm putting the next step up or the next step down. Like this. And but there's an extra condition. I want the union to be an interval. This just means that the staircases have to, or they don't have to overlap. They either touch or they overlap. They have to overlap. So when you take the union, I'll throw an example. And then the second condition, there's only two conditions, is suppose that suppose you have a bottom step, so that means you're below its neighbors. You're below its neighbors, or you have a top step. Or you have a top set, then what has to happen is VI plus 1 and VI minus 1 has to be disconnected. Or like not an interval, not an interval. Not an interval. Okay, and those are the two rules. Those are the two rules for a staircase diagram. So let me show you a picture over here.
Is that both? Is BI is less than both of those?
Yeah, if BI is below both its neighbors in this ordering. So this ordering and this ordering are unfortunately different. If it's at the bottom, these will turn out to be minimal elements. And then this one means that it's a maximum element. But let me just give you an example. And I like to draw this kind of in blocks. So here B1 is 1 through 4. And then I'm going to declare that B2 is 3 through 6. And then I can continue to stack them. So these are all increasing. 5, 6, 7, 8. But then what I can do is I can decide to go down. Oops. For example, if my next block is 8, 9, I can choose to put it up or I could choose to put it down. And the reason why I can put it down is there's space. So this one is above both of these. And when I take the union of them, there's a disconnection in the middle. So when you step down, you have to have space. You gotta have space between here. Otherwise, it can't butt up against this one that's 2 away, like this. And then I can choose to go up again. And these are allowed to be disconnected. So, this last interval, this just means that this one is not comparable to the other one because, it can't be a cover because, it does satisfy this one. It's the next one in the order, but their union is not. So this one can't be a cover. So pick any collection of blocks that, are shifted over like this. and then put a partial order on it that satisfies these conditions, which means, you know, you can stack them. So it generally means you can start stacking them up and down. And you just have to make sure that, you know, if you change direction, make sure you have a space. Otherwise, you know, you're not allowed. You're not allowed. And this is a staircase diagram. This is a staircase diagram. And can I erase? I'm a little sad. Maybe I'll. Which one should I erase? I think I'm gonna erase the middle. Or I can see it as a backward. Use the backward. So the theorem, and this is due to myself and William Slofstra, is that staircase diagrams on N are in bijection with smooth permutations. So these pictures correspond one-to-one correspondence with smooth permutations. On oh, do I have to go? Sorry, I have to do this. Type AN. This 1 through N is the Deacon diagram. So I have to do one more like this right here. So what's the map? What's the map? The map is okay. So this is what you do. So what I'm going to do is I'm going to select a maximal block in my diagram. So let's say this is B, and B potentially rests on other blocks. It might not. So this is B. This shaded region. The shaded region I'm going to call B prime. B prime can have potentially 2 parts. So you have B, which is the whole block, and you have B. And what I'm going to do is I'm going to define lambda B in this diagram to be the following. It's going to be the maximal element. And W of B intersect W of B. So what is W of B? This is the Levy permutation subgroup generated by B. So you have to imagine that like 3 through 6 is like, you know, the permutations generated by S1 through S6. So that's what this group is. B prime is a subgroup. What you're taking is you're taking the minimum length coset representatives with respect to this subgroup. You're taking this will have a unique maximal element, you know, relative of minimal length with respect to B prime. So to each B, you assign this element. Okay. And by the way, this element is isomorphic to. I'll just write that on the board. It's the partial flag variety. SL generated by B, mod the parabolic generated by B prime, like this. And that's what it is, like this. And this is what you do. So that B max in D. That B max in D. So that means it's a top block. So you have like 3 top blocks to pick from there. Then you define lambda of D recursively to be lambda of B times lambda of B minus B. You pick a dot. So this is a recursive definition where you select any maximal block and you write this element, and then you inductively put this thing right here, and so that gives you a permutation. And the theorem is that, you know, this will give you a smooth permutation, and this is 1-to-1. This is 1-to-1, and onto. Okay. And not only that, if I look at the Schubert variety, and there's going to be a projection map where I project onto, whoops, gosh. And this is going to have five, and this projection map is going to have fiber the other one. It's going to have fiber the other one. And in the fiber bundle that Ryan gives is exactly comes from this picture. Comes from this picture. Like this. Now these pieces are not Grassmannian, but they're isomorphic to full flag varieties. So any full flag variety can be broken down into a fiber bundle of Grassmannian. So the staircase diagram is basically sort of getting this collection is like sort of removing the redundancy of possible sort of iterated fiber bundles. That's what's going on. Okay. Now, like I can saying to make it through and not go through. So here's some comments on staircase diagrams. One thing to note is so when it comes to counting smooth permutations, it's sufficient to count these diagrams. And I claim that it's not easy to count the diagrams, but there are many techniques. So one theorem about this. The staircase diagrams are Catalan. And here's how they're Catalan. So if I have a staircase diagram that just goes up, then I'll label this x1, y1, x2, y2, x3, y3. So these are the distances of these spaces. That's what I'm gonna label that. And what you can do is you can get a dict path. X1, y1, x2, y2, x3, y3. So x1 is clearly going to be bigger than y1 because of the nature of this stacking going up. And just this the nature of these distances will always give you a dict path below the line y equals x. So this gives you enough to count increasing staircase diagrams using Catalan numbers. And then going up and down is just like, you got to do some extra work. But but this is the end, Catalan numbers, and then you go from there. Okay. So this tells you how to count it. It is basically use Catalan combinatorics and gets you rank. Okay. So now I want to go back to these examples. In particular, these two examples. What are these? What are these over here? So this subfamily in terms of staircase diagrams, they look like this. They're staircase diagrams given by single blocks, by singletons. And the singletons, when you think about RP1s, they're just that's like the flag variety generated by S1. Right? They're just P1s, and they're fibered over each other with respect to the diagram. Like this. So that's what you get. So and then here it's very easy to count because this is not Catalan, but basically you can do an induction every diagram of this size is you delete one blocks and that's its diagram previous size. And it's not hard, and then there's some overlap. So there's just a linear recurrence. So a generator function pops right out. For this one right here, so this is kind of the new work. So what do these look like? These polished ones. And by the way, this 312 in staircase world means avoids. It's like avoiding a S3. Yes.
How do you read the fiber bundle from the diagram?
Okay, so a top block, this will correspond to the Schubert variety, this is 1, 2, 3, so this is like the Schubert variety just generated by S3, which is a P1. This is what we're projecting onto. So this is so we're projecting onto this. And the fiber is inductively given by the staircase diagram when you remove the block. And then you have the rest of it. So to iterate the fiber bundle, you have to pick another maximal block. And then you just keep going. And this gives you the fiber bundle structure as P1s. Yeah. By the way, I'm iterating on the fiber here. And before I iterated on the projection, that's like how people like to think of iterated. But there's an associativity of, at least for Schubert varieties, there's an associativity where if you iterate on the fiber, you can associate it, regroup it so it iterates on the projection. So it's the same. Yeah. So back to this one. What is this? So it turns out that the staircase diagram for these polished ones look like this. They're basically going to be blocks where they're only allowed to overlap once, like this, and then you're also not allowed to go up twice, like this. You have to be going zigzagging back and forth, like this, and then so your pieces look like this. And then what you're allowed to do is you are allowed to sort of have these so with the non-overlapping, if you have something like this, you can put this on top or bottom. So it's like a union of pieces where if you have overlaps, they have to like this, and they have to come in segments where you can't go up twice. And what this means is that polished permutation corresponds to iterated fiber bundles. What are these right here? These pieces with 2 overlaps are partial flag varieties where you've only forgotten V1 and Vn minus 1. So it's like a V2 through Vn minus 2. And if it occurs on the end, this is like, you're allowed the V1, but you forgot the Vn minus 1. And if you're at the other end, it's like the reverse. So you're going to be iterated fiber bundle of things like this. And but this is not completely descriptive because you're also not allowed to, you're not allowed to go up here, let me tell you what, so these patterns have a meaning. So one of these means that you're not allowed to do a double. So one of these means avoids this, where you do a double overlap. And the other one means you avoid going up. You avoid going up twice with 2 overlaps like that. So you're sort of avoiding these types of things with these ones over here. Okay.
The strips can have varied lengths.
Yeah, the strips can be varied length. So you can have like 3 things, even with 1 overlap, but you're just not allowed to go up twice. But you're allowed to go up, down, up, down, up, down with overlap. Yeah.
And I can also have a disconnected.
Yeah, and you can have disconnected pieces. Yep. You can have disconnected pieces. Yeah. And then using this is not so bad. So the answer is yes, there's a generating function. It's 100% rational. And it's not bad. It's not bad. It's because these things, so you can enumerate these by basically controlling these gaps. So a piece is given by what these gaps are, because they only overlap 1. So you just have to enumerate those sequences, and then it kind of comes out. Okay.
Can you see which permutations are less than or equal to W from the staircase diagram?
It's a good question. Yes, but it's going to be it's not going to be very easy. It's not going to be easier than just straightforward, the straightforward way.
Okay, so it's not like the property 3 self-duality. That's not obvious from just looking at these kinds of.
No, when you avoid these, this is a very mysterious property.
Okay. Thank you.
Yeah. Yes. Oh, I'm over time. Okay, so let me just tell you in words without writing anything down what's happening here. So for these soup cases, what you're going to do so now you need something bigger than staircase diagrams. So what you do is to get bigger, what you do is you have to assign, so each one of these staircase items give you multiple Schubert varieties, and you do it by assigning like a different labeling. This is what I call labeling, when you assign to each block an element. So it turns out you can assign other blocks in a valid way that makes a fiber bundle structure. And this is what we call the maximal labeling, because we're labeling with the maximal element. But there are non-maximal labelings. And it turns out that like when you look at this category, for each one you have a whole Grassmannian. For each one of these, you have like a sum over possible Grassmannians to do this one, which means to each one of these you get like a partial sum of binomials. And partial sums of binomials are like very nasty to deal with in terms of like getting functions. But for this one, it's quite easy. You basically get one for every like sort of exposed bottom block, you get one Schubert divisor, and then you also have the whole Grassmannian itself. So like for this block, I would just assign 3 possibilities. This one also has 3, this one has 4, and you just go like that. And these weighted Cantal objects you can actually count. So that's what happens here. Okay. So I think I had a future directions, but maybe I'll just some more over time. I'm just going to stop now. Thanks for listening.